right, this is lesson 5-6, remainder and factor theorem. So it's going to feel a lot like the last lesson because we are going to be using some synthetic division. But really the idea is to figure out if we have a remainder. So we are going to use both the division and then we're going to look at it using this remainder theorem. So let's go ahead and synthetically divide. So putting this equal to 0, we're going to have 4 in our box. We're going to put our coefficients 1, -4, 3, and -5. We're going to bring down the first term, and we're going to multiply. We're going to add. We're going to multiply, add, multiply, and add. So 7 is our remainder. So this is not a factor, because we have a remainder here of 7. So it would look like x squared and then plus 3 and then plus 7 over x plus 4. So over here, if we plug in the remainder, then we want to, or evaluate, excuse me, for r, which in this case is 4, this number up here in the box, we're plugging that in to this and evaluating it. So when we do that, 4 cubed is 64, minus 4 times 16, remember do exponents first, plus 12 minus 5, so 64 minus 64 plus 12 minus 5. So that's 0, 12 minus 5, that's 7. Oh, well looky there, 7, so it's giving you the remainder. So we can tell that it's not a factor. So we just did the same exact thing, only we didn't have to go through the long division. So using the remainder theorem, you can determine if that divisor will be a factor without doing any division. So let's go ahead and practice that using this remainder theorem. So remember that we're using our r value. So that is when we hit this, put that equal to 0, r is -3. So we're going to plug that in, and we are going to take -3 cubed plus 3 times -3 squared plus 4. Want a shortcut? Type the dividend into y equals in your calculator. Go to the functions table by pressing second and then graph. And in that x column, find the r value and its corresponding y output. And then you can pretty much see if it's a remainder. So typing this into the y equals, and then going to second graph to that table, looking for this r value, -3, and looking for the y to see what that remainder is. So you can do it that way, and that's even quicker. So -27 plus 3 times 9 plus 4. So that's -27 plus 27 plus 4. Well, that's 4. So if there's 4 here, that means there's a remainder. So it's a no. This is not a factor of that. So I want you to try the next one on your own B, and then check when you're ready. All right, so let's go ahead and check. So plugging in, remember we set this equal to 0, so r is 9. So should have plugged in 9 for x and then simplified, and you get 114. So it's a no because you've got a remainder there. So let's try one more together. So this set equal to 0 would mean r is equal to +5. So 5 cubed minus 7 times 5 squared plus 7 times 5 plus 15. So simplifying that, 125 minus 175, and then plus 35 plus 15. So if we add that all up, we get 0. So this one is a yes, because we got 0 when we add all these up. So that means that this is a factor of that. So let's take a look at the next page. And we are determining whether x minus 3 is a factor of x cubed plus 4x squared minus 15x minus 18. Then we're going to find the remaining factors. So that's the additional piece here from what we did on the first page. So we have synthetic division. So what's left would be x squared plus 7x, I'm just bringing down the coefficients, plus 6. And since we have a remainder of 0, then x minus 3 is a factor of the polynomial. So if we multiplied x minus 3, which is our first part here, the binomial that we divided out, and that x squared plus 7x plus 6, then we would wind up with what we started with. So we're going to factor this. Factors of 6 that add to get 7, well, that would be 6 plus 1. So we have x plus 6 and x plus 1 and x minus 3. So now we have all of those, and you could refoil to check and see if you would get this, but you do if you multiply that all together. So that's what we're going to do here. We're going to take what they're giving us, we're going to factor that out using synthetic division, and then what's left we'll factor. And most of them will be shortcut, except for number 3. We'll take a look at that long method. So for the first one, we're going to take this out using synthetic division. So set equal to 0, 2 is what goes in the box, because that's what x would equal. So then we put our coefficients, 1, 3, negative 6, and negative 8. Again, they have to be 3, 2, 1, and none in order. Otherwise, we have to put a 0 in to hold that place value. So remember that. 2 times 1 is 2. Add. 5 times 2 is 10. Add. 4 times 2 is 8. Oh, good. That's a factor. It should be, because it's giving you a factor, so this should always be 0. So next is x squared plus 5x plus 4 that we're factoring. Factors of 4 that add to get 5 would be 4 and 1. And then don't forget that all the factors would include this one. So if we had to, we would add that x minus 2 to represent all of the factors. All right, I want you to go ahead and do the next one on your own. It is a shortcut method just like this one. So first use synthetic division, and then what's your remaining answer? What's remaining after you divide that out? Finish factoring, and then check your answer when you're ready. All right, so let's go ahead and check. So we should have a positive 1 in the box. We should have 1, 7, 7, and negative 15 as our coefficients. Bring down the 1. Excuse me. Multiply. 1 times 1 is 1. 7 and 1 add to get 8. 1 times 8 is 8. Add 15. 1 times 15 is 15. Add, and our remainder should be 0 since we are already given a factor. So last step, take that x squared, that 8x, and that 15, and factor it. Factors of 15 that add to get 8 are 5 and 3, so it's x plus 5 and x plus 3. And then don't forget to bring down the factor they already gave you. All right, so this next one, number 3, is the last one we'll do together, and it's the long method. And then I'll have you finish up number 4 on your own, and we'll check that one. So first step is to divide out this factor, negative 2, when we set it equal to 0. So 3, negative 4, negative 17, and 6. And bring down the 3. Multiply, add, multiply, add, and multiply. And we should get 0 as the remainder. There it is. So we have a 3x squared minus 10x plus 3. So see how we have this coefficient? So we're going to have to take the first times the last, 9, and then figure out the factors to add to get negative 10, which would be negative 9 and negative 1. So we're going to have a 3x squared, replace the middle with those two factors, and group. So pulling out for the first two a 3x, pulling out from the second group a negative 1. And then we're going to take that 3x minus 1 and put those in parentheses, and then the x minus 3. And then don't forget up here that x plus 2 goes as well. And there are our factors. So it's pretty easy when they give you one. So start on this next one. Divide out this factor using synthetic division, and then factor out the last little bit. And think difference of squares as you're working. All right, so let's check this last one. Setting this equal to 0, we would get a 3 in our box. Put the coefficients 4, negative 12, negative 1, and 3. Bring down the 4. Multiply 3 times 4 to get 12. Add. Multiply. Add. Multiply. Add. And then we get a 4x squared minus 1. So again, think difference of squares. So 2x plus 1 and 2x minus 1. And then our original factor they already gave us, bring that down as well. All right, so we're actually going to turn to page 26, and we're going to do lesson 5-7, and then we'll go back to the other sections in the same order as your notes after this lesson. So if you're not there, turn to page 26. This is lesson 5-7, roots and zeros. So we're going to determine the number and type of roots for a polynomial. So for this first one, consider the polynomial function. The zeros and roots of the function are -3, -2, 1, and 2. So then what were the factors? So if these are the zeros, then inside the parentheses, remember, it's basically opposite. So it's x plus 3, it's x plus 2, it is x minus 1, and it is x minus 2. So what are the x-intercepts of this graph? So here's one, -3, 0. Here's another one, -2, 0. Here's a third one, 1, 0. And then here's a fourth and final one at 2, 0. So for every polynomial equation with degree greater than 0, it has at least one root in the set of complex numbers. So this theorem doesn't seem like much, but it leads us to more important theorems here, which if it is x cubed, then we have 3 roots. If it is x to the 4th, then we have 4 roots. If it's x to the 5th, we have 5 roots. So the degree of the polynomial with one variable, this is the degree here, the largest exponent. So over here we've got some examples pointing to those zeros, which we've seen before in an earlier section. So if a polynomial has a degree of 3, it'll have 3 roots, places where the polynomial is at 0, and so on. So all we're going to do for this first one is just state the number of complex zeros each polynomial has. So here's the degree, 1. So how many zeros do we have? 1. Over here, squared, how many zeros? 2. So it matches that highest degree. So here's 5, should have 5 zeros. Over here, 4 should have 4 zeros. So for the last two, think about it. How many zeros would you have? Hopefully you put 2. And for the last one, 5. Not too hard, right? So let's take a look at the different types here. So using the fundamental theorem of algebra, we now know how many total zeros / roots a polynomial has. However, we need to keep in mind that there are different types of zeros and roots. There are rational. So for example, rational are the pretty answers, the roots that cross the x-axis and are easy to identify, like x equals 5, or even 1/2, or 0, or -2. Those are rational. Irrational are not as pretty, and they are not as easily identified. So maybe x equals plus or minus square root 5, x equals 4 plus or minus square root 3, or x equals 1 plus or minus 3 square root 6. And then we also could have some that are complex. These can be these can be sort of ugly answers because complex numbers include imaginary. So these are not always visible on the graph. The complex number system includes the rational and irrational. So a complex zero doesn't have to be ugly, but if it is only complex and not rational or irrational, then it will be an imaginary or ugly solution. So here, let's take a look at some examples. So we could have plus or minus 5i, imaginary. We could have x equals 4 plus or minus I square root 3, or maybe x equals 1 plus or minus 3i square root 6. So we also have to take a look at something called the conjugate. So only the sign in the middle is what's changing. So a conjugate is where you have that change in the middle of the binomial. And that is its imaginary part that the sign is changing on. So basically, if you have a root 2 square root 3, if that's a root, then you know -2 square root 3 is also, because we know it's plus or minus 2 square root 3. So here's the positive. We also have the negative that is a root. So over here, if this is a root, which one do we change the sign on? Up in the middle. So it's 1 plus square root 5, which is also a root, because we know it's 1 plus or minus square root 5. So here's the negative. We have to represent the other one as well. So try these next two on your own and then check when you are ready. All right, so let's go ahead and check. So if it's 7 plus 3i, then you should also represent 7 minus 3i. If it's negative 13i, then you should also have positive 13i represented as well. So let's go ahead and do some practicing. We are going to write all of the zeros, so finding all the additional ones that are not represented. So we basically just look for those imaginary or those ones that have the square root that have the sign. We also want to represent the other sign. So here we go. This one, 2 plus 3i, we want to represent 2 minus 3i as well. That one should also be in there. So over here, oh, there we go. We've got the plus. We also need to represent 3 minus square root 2. So on this next one, there's going to be 2 because there's an imaginary here and there's an imaginary, or not imaginary, but there's a radical there, complex number written there. So we want to represent both. So if this is negative, we should have a positive 7i. And then over here, this addition, we should also have subtraction. So both of those should be. Go ahead and try number 4 on your own and see how you do. Oops. All right, so let's check. So we should have not only positive radical 6, but negative radical 6. So anytime there's radical or imaginary, that's when we want to look to add that next, or that opposite. So 5 minus, we should have 5 plus 5i. Here, 4 plus radical 5, we should have 4 minus radical 5.